It's just taking second sine, second cos, second tan of a positive, correct? If we take it of a positive ratio, all of those three trig ratios are positive in quadrant 1, which the reference angle and the angle are the same, correct? So if you're ever looking for a positive or looking for a reference angle, you always take positive of it. Well, this is yesterday. Who taped this on? I think the boredom. Some people. Okay. So what we have to look at is we have actually 6 trig ratios we could use. I would never use a secondary, so I could use the 3 primaries. If I'm having a choice on which of these I'm going to use to find the reference angle of, I'm going to pick tan because it's 3. So if I want the reference theta, and once I get the reference angle, I just add it to 180 and I'll get my terminal rotation, right? I'll get that actual principal angle. So I have tan theta equals 3. So reference, why is it writing so terribly? Reference theta equals tan neg 1 of 3. And I don't have to make it negative because, or make it positive because it already is positive. And we're going to do them in degrees. This one in degrees. So we're going to make sure we're in degree mode. So I get, and it depends on what they ask for. I'm going to do to the nearest 10. 71.6 degrees. So that's this little piece here. So how do I actually get the angle, the rotational angle? Now that I have the reference. Yeah, because I drew this, because I actually drew the graph, or the angle, I know it's going to be 180 plus the reference angle because it's in quadrant 3. So I'm going to do rotational angle is going to be 180 degrees plus 71.6 degrees. Oops. Equals 251.6 degrees. So you can use any of the 6 trig ratios, right? Try it. Go second cos of positive root 10 over 10. Try that out. Go second cos positive root 10 over 10. Then go second sine positive 3 root 10 over 10. You get the same answer, right? Because you're getting quadrant 1 angle. You're getting quadrant 1 angle, quadrant 1 angle every single time you're taking a positive. So any of the 3 primary trig ratios you can use to get the reference angle. Does that make sense? And the reason why you take the positive is because then it lands you in quadrant 1, and quadrant 1's angle is the same as the reference angle, right? They're equal. So that's why I always take the positive. Okay. Number 2, bless you. Try and find the actual rotational angle of this one. So we can pick any of these. I'm going to pick cos because I'm going to be lazy and not even change it to a positive because it already is. So cos theta equals 3/5. If you use sine or tan, you have to make sure to take the positive, right? Always for the reference angle. So reference theta equals cos neg 1 of 3/5. So it's going to be 53.1 degrees. Okay. Now, that's the reference angle. That's this piece. I need from here to here. How do I get a quadrant 4 angle with a reference angle? Yeah. So I'm going to go the rotational. minus that, and I get 306.9 degrees. Now that's in degrees. I want you to give me it in radians. So you're going to have to change your mode. To go to your calculator, change your mode to radians, or you could just convert that. But I want to show you how you could do it with the mode. So if they wanted it in radians, you could just get it in radians. you could go cos, or sorry, second cos of 3/5, and you get 0.927295218 radians. How would you actually get the rotational angle now?
Subtract that.
Yeah, subtract that from 2 pi. So you could just convert this, or you could go and actually just do it in radians, right? And you would get 5.4 radians. You could go 5.4, or you could go rads, or you could go radians. I usually like writing a word behind it, or else just a number sitting there and I forget that it's an angle. Okay? Now we're moving ahead to these ones. There we go. Okay, I want you to give me the rotational angle of 3 and 4, please. This one in degrees. And this one in radians. The rotational angle. All right, so for the first one, we need the rotational angle. It's sine negative, but we're not going to do that. We're going to do reference theta equals sine neg 1. So inverse sine of 2/3 in degree mode in my calculator. And I get 41.8. And if you sketch out the graph, it's a heck of a lot easier to figure out the rotational angle. We agree? If you sketch where the heck it is. Because you throw the rotational angle in here, and you say, oh, boom, I need to, or sorry, the reference angle in here, and you go, hey, I need to go 180 plus it. Correct? So you get rotational angle. Don't short form on a test. I'm short forming because this is my notes. 180 plus 41, which is 221.8 degrees. Then this one I want in radians. So I do second cos of 5/13, positive, not 16. And I get 1.2 rads. But that's here. And I need from here to here. So this is pi, correct? So I'm just going to go pi minus 1.2. Well, not 1.2. What should I really be using? The full shebang. So the rotational angle is 2.0 rads. So when are we allowed to round? The very end. Okay? Formula sheet, unit circle, besties, bring them out. Say hello, holla. Okay, on the outside of your unit circle, you have coordinates, which are also known as answers. Are we allowed to flip answers?
Yes.
Yes. Are we allowed to flip angles in the middle? No. It should be like, you should be like zapped every time you try to flip an angle. Like, and then eventually you won't have that happen. It's like, you know, they did that with the mice. They would like feed the mice, and the mice would learn to like touch the buttons and stuff like that, and then not to touch. I think if we had little zappers and you went to flip the angle, it only have to happen a couple times. Not like a really zap you, just like a gentle, you know, like gentle. Not like that would only take 1 or 2 times. The little gentle one might take 6 or 7, but I think it's less mean. So maybe we could go that route. I don't know. That's aggressive. Cows are like hundreds of thousands of pounds. I don't think we're going to use that. Not hundreds of thousands, hundreds and thousands of pounds. They're in both. Weigh a cow. Really heavy. Have one step on your foot.
That one hurts.
You don't have toenails left if that happens. Cows are very heavy. You would be like, oh, you're massive. A calf is like 200-300 pounds when it's born. 100-200 pounds when it's born. More in the 100s. I'm getting aggressive with the 200s. The cows are over 100 pounds. Pick those babies up.
Cows in general are definitely.
I mean a calf. I'm going to Google the average calf weight.
Yeah. Okay.
I forgot.
Google implicitly.
I just did. So just in case someone's listening, calves average originally at birth 65, but by 1 year old they're at like 700 pounds, and then at adult weight 1,200, and bulls can be up to 2,500.
I don't know about that.
Fun fact.
It's not what people said.
I think someone used to make a montage called Clips.
Yes.
No. Okay.
Start with the rubber chicken.
Oh, that's where this all went wrong.
Yeah.
Okay. So we should determine the exact value. What is not an exact value? Decimal that does not, an irrational number is not one. One that does not repeat and does not terminate. We agree? So, on the outside of your unit circle, in those little coordinates, we have exact values, correct? So when it says exact values in trig, often you're going to run to your unit circle. Not run to it, it'll be beside you. You'll just lift it up. Or you could run. These are options if you're tired. All right, wake up. We need tan. So off of our unit circle, let's think about this. What is x? All the x's on the unit circle are the what? The coses. So if I'm a cos of an angle, I go to the x, boom, have an answer, right? If it's something that's outside of 0 to 360 or 0 to 2 pi, just find the coterminal and then poof, I have an answer. We agree? If it's sine, what do we pull off the unit circle? The y. If it's tan, what's the acronym for tan?
Tan your X box.
Tan your x box. So we're going to go the y over the x, the sine over the cos. And if you forget, your formula sheet says tan is sine over cos. Your formula sheet tells you exactly how to change all your unit circle stuff to be helpful. So tan here says sine over cos. Do you see that? So sines are the y's, coses are the x's. Boom, it gives me an answer. Cotan is cos over x, or cos over sine. So it's x over y. We agree? Secant is 1 over cos. So I could actually show it as 1 over cos and then flip it, or I could just know that secant is the reciprocal of cos, so it's just a flipped version, right? But this here tells you how to deal with your unit circle if you're stuck. Okay? So I need tan of pi over 2. So I go to pi over 2, which is at the top, it's 90. And tan, if I want to do the long version, tan pi over 2 is just sine pi over 2 over cos pi over 2. You can show this or just go right to the answers. It doesn't matter. What is sine at pi over 2? What is y at pi over 2? 1. What is x at pi over 2? What happens when you divide by a 0?
Your calculator freaks out.
Your calculator freaks out. And what word would you write? Does anyone remember?
Undefined.
Yes. So smart. Undefined. Now, some people will say no solution. Not true. Some people will say extraneous. Extraneous means I got a solution, it doesn't work, right? So they'll often say undefined here. So cosecant is 7 pi over 6. If I want to actually show this the long way, like I did up here, I can go 1 over sine of 7 pi over 6, which is just the answer flipped, right? Because I can flip answers, I can't flip angles. I can flip answers, I can't flip angles. So, what's sine at 7 pi over 6? Negative a half. So what's cosecant at 7 pi over 6? Negative 2 over 1, which is just negative 2. Okay, negative 300 is a lovely angle. What does it correlate with? 60, because you just add 360 to it. So actually, sine of negative 300 is equal to sine of 60, is it not? Because their y value terminates at the exact same spot, doesn't it? So I can just write that. That's actually a real statement. Sine of negative 300 is equal to sine of 60 degrees, because they terminate on the same arm, terminate at the same point, therefore they'll have the same y's and x's. So what is y at 60? Yeah. Look at all these. Aren't they pretty? You're going to do them all. But one thing, Cos 225 degrees with this squared in it. The reason why they write it that way is because if they said cos 225 and put the squared at the back, the 225 would be squared. I don't want the 225 squared. I want the cos 225 all squared. So they put the squared in bracket. They put the squared like this. If you go to type it in your calculator, the moment you press cos, say you want to check these, because you can check every single one of these. Type tan of pi over 2 into your calculator. I'm pressing tan. I slap my hand and I say, what mode do I need to be in? Radians, right? I put pi over 2 in and it'll get mad. So every single one of these, if you type them in, will get you a decimal version or the exact version if it's like -2, right? But for cosecant, you have to type it in like this because you don't have the button for a cosecant button, right? You have to type it in as 1 over sine, yeah?
Just curious, what is there any like reason for the secondary trig ratios to exist over the primaries?
Yeah, they're used for totally different things. And you'll see in calculus where some of them are used for. But for right now, you're just learning about them, and then you're going to use them. So when you get into advanced calculus, you use all the different secondary trig ratios for different things. Because they come up with totally different graphs. And they've asymptotes and stuff like that. All right. So, if you press the cos button, just press the cos button for me. What immediately happens? Okay, so how am I going to put the 2 in between the cos and the bracket? Trick question. You're not going to. You're going to call me over and you'll be like, Lepp, I can't, it doesn't put 2 in. Or you're going to put the 2 in and it's not going to work. It's going to be like, what is this person trying to do to me? Okay? So, with a calculator, it immediately pops open a bracket. This squared, all it means is I have cos 225 squared. It just means that answer is squared. So if I wanted to type this into my calculator to see actually what the answer was, I would have to go cos, and then the bracket opens up, 225 degrees, and then I would square the whole thing. That's the exact same. These are equivalent. Okay? So you try them out, and then you're checking them with your calculator. You're trying them out, checking your decimals with your calculator. So you should know if you're getting them right or not, and call me over. So secant of 60 is the same as 1 over cos of 60. And what is cos of 60 degrees? So secant is 2 over 1 or just 2. So I would type that in as 1 over cos of 60, right? That's how I'd have to type it in. And I'd have to be in degree mode. Okay, cos 150. 150 cos is? Sine of 315. Sine of 315 is negative 2 over 2. Because sine in quadrant 4 is negative, right? And y's in quadrant 4 are negative. Okay, sine negative 30 is the same as sine. Yeah, but it's the same as sine 330. So I add 360, which is the same as negative tan 240 is the same as sine 240 divided by cos 240. But this would cause me to stack fractions, right? So I'm not going to write them stacked. Once I get a fraction, whether it's in the numerator or the denominator, I write them side by side with the division sign so I can flip, right? Every single time. So if ever you go to write a fraction and then you know it's in like an actual fraction, a fraction embedded in a fraction, slap them behind me like, no, 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 no. Don't write it like that. Write it sideways so I can flip and multiply, right? Okay. So at 240, what's my answer for sine?
-2.
And then for cos? Now they're both negative, which makes sense because tan at 240 is going to turn out to be positive, correct? Because tan in quadrant 3 is always positive. So I would get negative root 3 over 2 times 2 over negative 1, which is actually negative or positive root 3. Just so you know, what reference angle is that? 240. What reference angle would 240 have? 60. Yeah, it'd be 60, right? The reference angle would be 60. All tans of 60s, all tan 60 degree reference angles will end up as plus or minus root 3. Just a little side note. Now, you don't actually need to know that because you could find it every single time, but it is helpful to know that any tan of 60 is plus or minus root 3, right? Depending on what quadrant you fall in. Because you're always going to be doing root 3 over 2 divided by a half, right? Whether it's positives or negatives. So the sign will change depending on the quadrant. All right, this one is tan 480, which is the same as tan 360, 480 minus 360, sorry, which is 120, which is the same as sine 120 divided by cos 120, which you don't have to show all this work, I'm just proving a point. What's sine at 120? Root, yeah, divided by negative a half, which is root 3 over 2, times negative 2 over 1, which is negative root 3. Because 120 has a 60-degree reference angle, right? And 120, tan at 120 is in where signs are all positive, so I know it's going to be negative root 3. So if you have that, know that all the 60-degree tans are plus or minus root 3. Actually, it's fast to do answers too. Okay, cos 225 is?
Negative root 2 over 2.
Yeah. And then we square it. When we square a negative, it becomes positive. We square a square root. Square root goes away. And we square 2.
4.
We get a half. Sine 5 pi over 3 is negative root 3 over 2.
Yes.
How do you say sure? I saw you all have answers. All right. Tan 7 pi over 6. You should be, because you should type sine 5 pi over 3 in radians into your calculator. Then you got negative 0.8660 blah, 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 which is root 3 over 2 in irrational form. And then you would be so confident, you'd be like, Lepp, it is negative, you know?
Still did that. Don't have confidence.
Come on, you're smart. Have confidence. Okay. Smarter than I was in high school, let's just say. Okay, sine of 7 pi over 6 is? Negative?
Negative 1 over 2.
Yeah. Cos of 7 pi over 6 is negative,
Root 3 over 2.
which is negative a half, times negative 2 over root 3. These cancel, the negatives cancel, so I get 1 over root 3, which rationalizes root 3 over 3, which is another fun fact. That the 60s, tans of 60s are plus or minus root 3. This is a tan of 30. So another fun fact is tan of 30-degree reference angles or pi over 6 reference angles are always plus or minus root 3 over 3. And the one great thing about radians is the moment it has a 6 on the bottom, that's a 30-degree reference angle. Because that's pi over 6. Okay, we have cos of negative 2 pi over 3. If I take negative 2 pi over 3 and I add 2 pi to it, I get negative 2 pi over 3. I hate making my writing so messy today, but whatever. 6 pi over 3. So it's the same as 4 pi over 3. So we're going to look for equals cos of 4 pi over 3. And we have to put the equal signs down because if you don't put the equal sign, if you don't say that this cos equals this cos, then they might think you're just giving the answer to this one, right? So you have to say cos of negative 2 pi over 3 equals, awesome, I'm near something, and it's equals cos of 4 pi over 3, which equals negative, see, much more belief, I like it. All right, sine of negative pi. If I add 2 pi to negative pi, I get sine of pi. Just in the same quadrant, or same spot. And what's y at pi? 0. So negative 5 pi over 3 plus 2 pi, or plus 6 pi over 3 if you make a common denominator, is just pi over 3. So this is the equal to cos of pi over 3. Make sure you have your equal signs. And at pi over 3, cos is? This is just tan 2 pi over 3 squared. Sorry, the whole thing squared. All right, like that, 2 pi over 3 squared. That's why you need the brackets. So at 2 pi over 3, what's tan? It's root 3, because look, it's a over a 3, so it's a 60-degree reference angle. And tan at 2 pi over 3 would be negative, right? So it would be negative root 3. And you square it is? We'll wait for you. So you can show that tan 2 pi over 3 is sine 2 pi over 3 is cos 2 pi over 3. Divide them, flip it by multiplication, get the negative root 3, then square it, totally fine. But if you have your 30 degrees and 60 degree tans memorized, it does make your life a little easier sometimes. Okay? Your homework. All we have left is one lesson in it's 4.4. It's going to be solving. I've lost the textbook. So for B and D, you do the rotational angle. Yesterday I made you do the trig ratio for 5D. 1, you're doing what we did above. 5, you're finding the rotational angle we did before. 6, you're just telling me if it's positive or negative where it's sitting. You don't actually give the exact value. And 9 is exact values. More work.